about that just the other day. We learned about how an equation can be graphed. We can either plug in points until we find one that works, or we can use the points that we were given and maybe the slope to graph it. And that has been how we have graphed a linear equation. Well, a system is generally two, sometimes more, linear equations. A system is usually two, but sometimes more, linear equations. There are three pictures there on page 124 that I want you to look at really quick. And those pictures are various scenarios of a graph that you might encounter. Like, let's just say letter A, it is two lines that are graphed and they intersect one another. And another scenario, B, is two lines that are graphed and appear to be parallel. In other words, they will never meet. And in C, we have two lines that actually share the exact same locations. They're just written differently. That is another scenario. So you've got intersecting, parallel, and coinciding. Those are your three scenarios. Coinciding, by the way, are also equivalent. Anyways, just a couple of pieces of terminology for you. All right. Don't worry too much. Top of page 125, there's a couple of different ways that you can transform your systems so that you can solve for them. And the best way to do it is to practice it. So I'm going to go ahead and walk through how you might solve a system and then be able to work with it. So here's my first one. This is my example one. Solve this system. In other words, you're looking for a solution that would fit both. There are a few different ways that you can solve systems, and it really depends on what you're given. I really like the method I'm about to show you, and that we'll call method 1. And we'll call it the linear combination method. The purpose of which is to combine both systems, which then cancels out one variable and allows you to solve for the other one. Once you have the other one, you can plug in and get the one you need. So it would look something like this. First, look at it and see if anything within one equation is opposite of the other. And in this case, the y's are actually exact opposites of one another. You guys able to see that? One is a positive y and one is a negative y. Okay? If I combine just by adding these together, I now have, so I'm going to combine because y's will cancel each other out. I will now have 5x equals 15, right? 0y, the y's canceled out. If I solve for x, I uncover that x equals 3, right? Okay. Now that I have x, plug in and solve for the other. It doesn't matter which one you plug into. Either one will give you the right answer. So 2 times 3 plus y is 7. 6 plus y is 7. So it looks like y has to equal 1. Would you agree? To be sure, we've already used this one, let's test it in the other one. 3 times the 3 that we came up with for x minus a positive 1. Does that also equal? Does that work? Yes. So we have our solution set. X has to equal 3, y has to equal 1 in order to solve both systems. That is the linear combination method in a nutshell. Go ahead, question.
In the second equation, where do you get the other one? Not that one, the other one.
Where did I get the 1 from? Right there. I tested the y that we got from plugging in the x that we got from solving the combination.
Oh, okay.
So first you combine, and you combine because these canceled out and I got my x value.
Yeah.
Then I plugged in my x value and I just chose the first one and solved for y.
Yeah. Okay.
Then I verified that that y value was true by plugging it into the other one. If it wasn't, then something's wrong somewhere. Okay, don't worry, we'll be practicing more of these. All right, here's another one. And this is still kind of example 1-ish. And if I wanted to graph it, I could. I could graph it. And I would know that both of these would somehow intersect at this line. I would know that both of these somehow would intersect. Now, most of this does not tell you to graph it. Most of the assignment doesn't even have you graphing it. It just has you solving it. So you won't be doing a whole lot of graphing. All right. Here's another example. Same kind of problem. 2x plus y equals 1. 2x plus 3y equals 7. All right, are there anything that are exact opposites of one another? Well, those x's, they're identical. And this is a y and that's a 3y. So there are no opposites. Can we create an opposite by multiplying one equation? And actually we can. It doesn't matter which one, but if we multiply one of these equations by a -1, like let's just say this equation by a -1, it now becomes -2x minus y equals -1. Was I able to create an opposite? Yes, I was, by multiplying one equation by something that made, well, it just so happened to make the x an opposite. So here's the new version, and here's the old version of the second equation. And we are now going to combine, and it looks like we're canceling out our x's this time. Looks like we're canceling out our x's. 2y equals 6, so it's telling me y should be 3 as a solution for both of these. Plug in your y value and solve for x. Plug it into one of the originals. I'm going to plug it into the second one. 2x plus, bye-bye there. 3 times 3, 3y is 7. 2x plus 9 is 7 minus 9. 2x equals negative 2. Looks like x equals negative 1. So right now, I believe my solution set is negative 1, 3. But I'm going to verify that by plugging in the negative 1 in the other one. So I'll plug it into the top one using what we believe to be the solution. 2 multiplied by negative 1 added to 3, does that equal 1? Negative 2 plus 3, does that equal 1?
Yeah.
Then you have a correct solution. Okay, those were 2 examples of the linear combination method that allowed us to cancel out something by making one thing the opposite of the other. Okay, here's another example that I want you guys to see because there's another scenario that might exist. All right, here's another example of a system that we're going to solve. Can I do anything to make the x's opposite of one another or the y's opposite of one another? Can I multiply one equation by something? What, Dylan? Yep. If I multiply the bottom equation by 3, the bottom equation becomes 9x plus 3y equals 15. That's the new version. It's just like renaming a fraction. It's still the same value. Like those x variables, how I said they all needed to be integers. I know technically it's the same value, but because of the rule, you have to make them all integers. Anyways, we just renamed the bottom equation by multiplying it by 3. Dylan saw that by multiplying it by 3, his positive y became a positive 3y. When combined with the other equation, it'll cancel out the y's and let us solve for x's. Giving us combination 11x is, what is that, 22? Which means x is 2. If x is 2, let's plug it in. I'm going to plug it into the first version. 2 multiplied by 2 minus 3y. 4 minus 3y. 3y equals 3. Looks like y is equal to negative 1. If my arithmetic's correct. So that means we believe our solution is 2, negative 1. 2, negative 1. We're going to check it in this one just to make sure we're right. 3 multiplied by 2 added to negative 1. Does that equal 5? Good deal. That checks. There's another scenario in a linear combination method where the only way to find something to cancel out is to create 2 completely new equations. Sometimes you have to multiply both pieces by something to make a something that cancels. That's very doable as well, and we're going to see that here as we go along. Here's another example. This one will coincide with example 3. I kind of did example 2 with you already. Those last few really fit with example 2. And I'm still talking about the linear combination method. Here's their example 3. Here's mine. Notice there's nothing that will quickly change everything. But the 3 and 2 are small, would create a 6 somehow, and 2 times 5 would create a 10. So I am going to somehow make this y value 6's. That one's negative, that one's positive. If I multiply the top piece by 2 and the bottom piece by 3, my y values now become 6's, being able to cancel each other out. So here's my first new equation. 4x minus 6y is 6. My second new equation, 15x plus 6y equals 51. Betcha 51 is a multiple of 19. Yep. Combining cancels out our y's. 57, I mean. So x is 3, right? Am I right? Okay, so if x is 3, let's plug it into the first one and solve for y. 2 times 3 minus 3 times y is 3. 6 minus 3y is 3. Minus 6. Negative 3y is negative 3, so y has to be 1, right? Looks like y is 1. So right now I am believing that my solution is 3, 1. I'm going to check this in the second equation using the values in question. 5 times 3 plus 2 times 1 equals 17. Good deal. We're good. You can even test these values in the new equations. They're all equivalent. This one's equivalent to his mothership up there, and this second one is equivalent to its mother. All we did was multiply it by 3 to change it. I've focused so far, my friends, on something called the linear combination method, okay? There is another scenario, and it's called substitution.
Is it easier or just?
It depends on the problem. Yeah. Some of them you're going to say, well, substitution's easier. Sometimes you're going to say combo is easier. It depends on the numbers you're given. So while I did those examples, I did not do the substitution method because I feel like you don't want to do them both at the same time. So substitution method is solve for one of the variables and plug in accordingly, and I'll show you what that looks like. Look at example 2 with me, the middle of page 126. Example 2. Example 2 gives you the system x minus 2y is 5. 4x plus 3y is 9. So here it is. I'm actually going to use it because this is a really beautiful equation. It works really well. Okay. If this works really well, if one of the coefficients is a 1 already. Notice that we have a 1x. Minus 2y is 5. If I take this first equation and I solve it for x, it would look like this. X equals 2y plus 5. You see that? In the first equation, solving it for that first, for x, gives me this. If I plug this value for x right here, and then solve for y, I have begun solving my system. And it'll look like this. 4 multiplied by, there's the x value, 2y plus 5, plus 3y. Now all we have is y's. It's easier to solve when you only have one variable. Looks like I have 11y on the left and negative 11 on the right. Looks like y equals negative 1. Substitution. I solved for a variable. I solved for the x value. Solved for x. Plugged in right there. Solve for y. Now I have a y value. I'm going to plug it into a nice easy version. I'll plug it in right here and get what x actually is. X minus 2 times negative 1 equals 5. Negative 2 times negative 1 is a positive 2. So x equals 3. So I believe I have 3 negative 1. Is that correct? Hallelujah. Okay. When you do these, I highly recommend you read through their notes, read through your notes, practice, practice, practice. This is not intuitive. It does not come easy. This is substitution. I actually feel like substitution is easier more quickly. I don't know how to explain that, but it just makes sense faster. I do need to move on to example 4 and 5. Examples 4 and 5. These are relatives of your friend, no solution and all real numbers. You remember them from Kentucky? Well, example 4 and 5 are relatives, except we're talking about systems. Solve this system. Here is my example. 2x minus y 7, 4x minus 2y equals 9. I'm a real big fan of the linear combination method, and right off the bat, I want to multiply this by a negative 2 so that my x's cancel out, which this creates negative 4x plus 2y equals negative 14. You guys see how I did that? I chose the negative 2 because that would cause this to be the opposite of this. Incidentally, it also causes the y's to cancel out. Look at this. Combining everything, 0 equals a 14 and a 9. Negative 5. That's not true. That means there is no solution to this pair of linear equations because they are parallel lines. If you tried to do the substitution method, like you solved for y or something like that, you would still find that there is no solution. They are parallel lines. Yes.
So if we have a question like this, what would you want us to put for the answer?
No solution. Yep, no solution. The last thing. So this is your no solution. Here's example 5. And I know it's been a long lesson, and you're going to want to rewatch this and practice. Here we go. 2x minus 2y equals, lost my place, 8. And then I have y equals x minus 4. This isn't quite as elegant or as pretty as the other one. Since it's already set up as y equals, this is a perfect opportunity to substitute. So if y equals x minus 4, substitute it right there. And it'll look like this. 2x minus 2, x minus 4. We substituted the y equals value into the other equation. And it looks like this. 2x minus 2x plus 8 equals 8. These cancel out. 8 equals 8. Is that true or false? True. This is true. It's always true. 8 always equals 8. That means these lines are not perpendicular. They're not like the opposite of this. They are coinciding, which means they are the same line. They are the exact same line. They are the exact same line. Whenever you find they are the same line or they are coinciding, they will say to you, the directions in this say, if the system has an infinite solution set, which it does, if it's the same line, then whatever solves one will solve the other, and that's an infinite number of numbers because it's a line. Say infinite and give 3 solutions. So what would give 3 solutions to this? Well, you would just have to find out what would give 3 solutions to this, and it would work for that as well. Y equals x minus 4. I'm going to use this easy one to give 3 solutions. So, and I'm just arbitrary. You could have chosen the other one. It's just harder. This one's easier. If x is 0, y is negative 4, right? Would you agree?
Yeah.
If x is 1, y is negative 3. And if x is 4, y is 0. That works here. The question is, does it work here? It better. 2 times 0 minus 2 times negative 4 equals 8. It sure does. And if you kept checking, you would find that they all do work. Not everybody is going to have the exact same examples, and I don't care about that. Doesn't matter.